Okay, so hello, I'm Adam Chapaula. I'm pleased to be chairing this final session of the day on formalized mathematics. And our first talk is going to be a remote one by Floris on formalizing the H principle and sphere eversion. So take it away, Floris.
Thank you very much. Yeah, I'm sorry I couldn't participate in the conference in person, but I'm happy I can still present like this remotely. So I will be talking about formalizing some very deep geometric problems in mathematics, indeed, as the title says, sphere eversion and the H principle. So many formalizations of mathematical theorems focus on algebra or discrete mathematics. Not all of them. There are some geometric formalizations, but there is a significant focus on the more algebraic and discrete parts. And in this talk, I will present a very geometric proof. And that raises some potential challenges because in a textbook, a proof like this might be given using a picture, or maybe some geometric intuition is invoked, and that can be given instead of the details of certain proofs. So that is a potential challenge to overcome. And the particular problem I want to focus on is sphere eversion. And the question of sphere eversion is, can we turn a sphere inside out? And we have to follow two rules for this challenge. The first is that we cannot tear the sphere in pieces or have tears, and we cannot have sharp creases. So we cannot bend the sphere into a sharp edge, but we are allowed to self-intersect the sphere. So the sphere is allowed to go through itself. So if we say this mathematically, we start with the inclusion map from the sphere S2 into R3, so just a map into the unit sphere, all the points with distance 1 from the origin. And we want to transform it in such a way that at every step in the transformation, the map is an immersion. And so here I've given three equivalent characterizations of what an immersion is. So the first is that F is locally an embedding. So that means that locally, if you just map F on a small disk on the sphere or small region, then its image under F is always a two-dimensional surface. And the last equivalent characterization is that the total derivative of F is injective at each point. So this sort of captures the intuition of almost embedding a sphere into the space, except that it is allowed to self-intersect at points. So the second question you might ask is, what do you mean exactly by the words inside out? So what we want is that if we sort of color the inside of the sphere and the outside of the sphere, then after the eversion, like those colors are swapped. And mathematically, like the sphere is just an infinitely thin set of points, so there's not a mathematically precise way of saying it. We cannot color the inside or the outside. But what we can do is we can look at the orientation of the sphere. So if we consider the antipodal map, so that is the map from the sphere into the real space that sends the points x, y, and z to minus x, minus y, minus z in the space. And so you can think of this as reflecting the sphere three times, once along the x-axis, once along the y-axis, and once along the z-action. And every time you reflect, you reverse this orientation. So this antipodal map is a composition of three reflections. So that means that we reverse the orientation. And then it's a mathematical fact that if we start with inclusion map, which is orientation preserving, and we end up in the antipodal map, which is orientation reversing, then such a map, such a transformation must interchange the inside and the outside of the sphere. If we sort of, we can make that mathematically precise if we thicken the sphere by crossing it with, by taking the product with a small interval. But so this gives us a nice formulation of sphere inversion. And here you can see, hopefully, an animation of the sphere actually being inverted. So the answer is yes, we can invert a sphere. And this was proven in the 50s by Smale. And so the formal, precise statement of this theorem is that we can find a smooth transformation of immersions from the sphere into R3 that starts at the inclusion map and ends at the antipodal map. And so this is a very counterintuitive result. Before this was proven by Smale, like mathematicians, or there were some mathematicians that thought that this was clearly impossible and not at all doable. And you can also see in this transformation that it is not at all obvious in this animation. It's not at all obvious what is exactly happening. At least if you just look at it for a little bit. But you can sort of see that there's these thickenings of parts of the sphere that are used to avoid the sort of the points you want to avoid, the places where a map like this would not be an inversion, not be an immersion. So I formalized this together with Patrick Massot and Oliver Nash. And one thing we could have done is just give an explicit construction, like the video I just showed, parameterize it, and show that this function satisfies the properties. But that would not be very satisfying, and like it would not be like a reusable result for other mathematical theorems. So instead, we we use a mathematical technique called convex integration, which I'll explain a little bit more in the next few slides. And this is a very general technique that can be used to prove a much more general theorem. And that is the theorem reprove is a deep result in differential topology. And it's the homotopy principle that Mikhail Gromov originally wrote down and proved in the 70s. And so the homotopy principle is abbreviated H principle. So the homotopy principle gives a very general technique to construct solutions to partial differential equations. So a partial differential equation is just any, I mean to say partial differential relations. So not just equations. So partial differential relations are actually more general. So a partial differential relation takes a map and it can provide any condition on the input value, on the output value f of x, so if the input value is x, and on any first order partial derivative. We only do this for first order differential equations. So this triple x, f of x, and the derivative of f at x, like a partial differential relation is any set on triples like that. So it's a very general notion and includes, for example, all partial differential equations. And with this homotopy principle, we can prove sphere inversion as a corollary, because sphere inversion says that like certain maps have to be immersions, and that is a condition on the total derivative of f, because it's saying that the total derivative is injective. And so, although the original proof was given by Gromov in the 70s, we actually followed a proof by Melanie Theillière from 2018, who simplified the implementation of convex integration. So what is convex integration? So consider a function from the real plane to R3. So we view this real plane maybe as some patch of the sphere. and we map it, this patch of the sphere, into R3. And maybe this map is not yet an immersion, but we want to change it into an immersion without changing the function too much. So we want to find an immersion that is sort of close to F. So how can we do this? We can do this by first by looking at each partial derivative of F in turn. So we can first look at the first partial derivative of F and require that it is non-zero. And if it is zero, change it a little bit. And then we can look at the second partial derivative of F and ensure that it's not collinear with the first partial derivative of F at like any particular point. And if we do that, then the total derivative is injective, and that is then we exactly get an immersion. So more generally, we want to say that in each step we have one of the partial derivatives, and we want to require that it lives in some open subset omega x. And now the key ingredient of convex integration is that we assume that there's some family of loops. For each point in the domain of F, there's a loop gamma x. And we require that this gamma x has two properties, namely that it always lives in this open set omega x, and it has at average the partial derivative of f at x. And so recall that this omega x for our immersion case, for our first partial derivative, the omega x is just the complement of 0, because the first partial derivative can be anything but 0, and the second, the omega x for the second partial derivative is just the complement of any one-dimensional subspace in R3, namely generated by this first partial derivative. Okay, so one of the main parts of the proof is actually proving that these loops exist in the more general setting of the homotopy principle. And what's interesting is that a necessary condition for the loops to exist is that these partial derivatives must lie in the convex hull of omega x. So the convex hull is sort of is the smallest convex set containing omega x, and a convex set is a set where that contains a whole line segment as long as it contains its endpoints. And so this fact that the partial derivative must lie in the convex hull, that is the reason why the word convex is used in convex integration. And so the integration part is next. So once we have these subsets and we have these loops gamma, then we can write down this formula, which might look a little bit daunting, but actually isn't that bad. So we take a very large natural number n, or well, it doesn't have to be natural, but a very large number n, and then we map x to f of x plus this modification. And this modification is sort of using this family of loops to sort of average out the jth partial derivative of f. And actually, if you it's a quite simple exercise just by computing the derivatives of this formula. That if you take that the g has all the properties we want. So the jth partial derivative of g is a value of gamma at a certain point, or at least approximately equal to that, which lies in omega of x. So we have this fact that the jth partial derivative of the new function lies in omega of x. For all other partial derivatives, we really don't change the partial derivative very much. And g is also close to f. So that follows from this formula. And so for the immersion case, we can use then this g, and we have to repeat the process first for j equals 1 and then for j equals 2 to get an immersion. But actually getting this transformation of immersions is a bit more complicated because we have to do it for the whole transformation at once. So for the homotopy principle, this is a statement for maps between manifolds. So originally, when we wrote our CPP paper, we weren't quite finished with the version for the maps between manifolds yet, but we only finished it for maps between vector spaces. But after that, we continued with the project, and now we actually also finished the general case for maps between manifolds. And so to give you a sense of the scale of the project, it's about 15,000 lines of code. And we also made over 140 pull requests to Lean's mathematical library MAVLib, improving the various theories about convexity of sets, parametric integrals, differential geometry, and many other topics. So the project was proposed by Patrick Massot about 3 years ago, but we really took off in the last year of the project. So it took us about a year to work on it part-time. So here's the final statement. So this is or at least of the sphere version. So it says that there's a function f parameterized by some real number of maps from the sphere into R3, such that if the function f is smooth in both arguments, and with smooth I just mean infinitely often differentiable, and at 0 we get the inclusion map from S2 to R3, which is written with CoE for coercion. At 1 we get negative the inclusion map, and at every point we have an immersion. And finally, I want to tell you a bit about one of the tools we used during the project. So we wrote, so at the start of the project, Patrick Massot wrote a detailed blueprint of the proof we were going to follow, but written in more detail than you would normally find in a mathematical textbook. This is a technique that is used also for some other big formalization projects. And what was interesting was while we formalized, we sometimes tweaked the statements of lemmas a little bit, or we changed the proof, and sometimes even we noticed that like some lemma was not quite strong enough to do the next step of the proof. And so we updated the blueprint while formalizing. And so now we have, after we finished the project, we have a blueprint that with an aligned LaTeX and formalized proofs, where each lemma statement and the proofs are aligned with each other. And the interesting thing is that, like, for some of these lemmas, it's really tricky to exactly formulate the lemma right, so that it's strong enough to do the next step of the proof, but also that the lemma is actually true. And sometimes we have to reformulate certain parts many times. And so the main benefit of this document right now is that we have very precisely written intermediate lemmas with very carefully written down all the conditions that need to apply and the precise result we have. And we don't have any hand-wavy terms or hand-wavy things like, well, for example, the things I wrote on the slides of convex integration, I used like phrases as sufficiently large, and I used the approximation sign. And these are very common in proofs of mathematical textbooks about this topic. But now this blueprint gives a very nice way and a proof in a very detailed manner. Thank you for listening.
Okay, so we have some time for a question or two. Yes.
Hello, this is Yves Berthaud. You said the proof is a geometric statement. I understand how the statement is geometric. We even had an animation. But are there parts of the detailed proofs where people usually just do a drawing and you had to express this drawing into formalized text?
Yeah, that only happened. So, for example, one thing, like for the one step in the proof is under certain conditions to construct these families of loops gamma, and that is a very geometric argument where you start with some geometric condition that maybe some map lies in the convex hull of some set, and then you have to like smoothly, depending on a parameter, find these families of loops with all kinds of coherence condition, and then you have to like if you have and you have to glue certain of these families together on larger and larger domains, and some of these proofs of, for example, of gluing two of these families of loops together with very particular conditions. In one book we looked at was just a list of 4 pictures and then maybe 1 sentence explanation. But there's actually quite some subtleties in that proof.
Let's see. Did anyone else want to inject a question, or should I hand the mic back to Eve? I'd also like to invite the next speaker to walk up and start setting up. Convenient benefit of switching from virtual to in-person. Going once, going twice. Any other questions? Okay, mic goes back to Eve.
In the initial statement, you said you wanted the derivative to be continuous, and in the final statement, you say you need the function to be smooth. And you explain the smoothness as being infinitely derivable. Isn't that much stronger?
So sometimes the share version is only written for continuous things, but in fact all the final results is only for smooth maps. So require that the theorem we formalize is this one where there's a smooth transformation. So we have this smooth transformation that is infinitely differentiable, and yeah, that is stronger in general. But luckily, like you can approximate smooth functions by continuous functions, and that is also what we used during part of the proof. Where for part of the proof we only work with continuous functions, and then at some point we use an argument called partition of unity, and then we can approximate the continuous function by a smooth function.
Looks like we have one more question here.
Are there any abstractions that you had to invent for the formalization that don't normally appear in textbooks because they're hand-waved or they're sort of a little bit going along with they just usually present a picture, but specifically any sort of like structures or abstractions?
Let's see. I mean, we had to. There were some things where we had, for example, a library of. We defined a theory of loops and families of loops, and we proved like a whole API for this. And I mean, of course, you wouldn't normally see that in a mathematical proof. One of the constructions we used for the for like combining loops is concatenating 2 loops, but in such a way that the midpoint where you transition from one loop to a next loop can be any parameter from 0 to 1. And we proved it under very general settings when such a concatenation is still continuous. What conditions you need to require, where you have to be very careful that if the sort of midpoint is 0 or 1, you have to require some things to not continuous but to be differential. So there was a little bit, but the big picture of most of the proofs was generally correct, and we could use like the mathematical concepts in those proofs.
Okay, let's thank Floris again.